Hi, welcome to Solving Science. The reason you can't see me because you have sun glaring through the glass into your eyes is because today we're talking about the Richard Feynman glass reflection paradox. So what I'm going to do today is tell you about this paradox, and then I'm going to tell you how I think general expanse tension theory can resolve it. So let's get into the details. Richard Feynman, rock star legend of the physics world of the 1960s, 70s, 80s, someone who really started to make sense of quantum mechanics. But in 1986, in his lectures at UCLA, California, he left us with a paradox, which has survived still as a mystery for 50 years ever since. And the paradox goes like this. If you shine light at a glass surface, you might have typically 4% reflect off the surface of the glass. Okay, that's fine. But if you start adding more and more glass in layers and actually increase the bulk of material glass, the reflected amount of light, the intensity of reflected light, can increase to 16% of the incident ray that strikes the glass surface. Now this is where it gets weird. If you keep adding glass, that amount of reflected light can then drop again to 4% and keep adding glass and it can increase to 16% and you get a sinusoidal wave pattern of light coming out of the reflected glass. Now that's strange. The reason why it's strange, the light reflects off the surface of the glass, but it implies the photon of light that reflects has some kind of innate knowledge or understanding of the thickness of glass in either the bulk of the material. Now the paradox gets even stranger because if you then start adding bulk material and backing material, you can add opaque plastics, high dense plastics, and solid materials in the back. And again, the light reflected from the front surface implies an innate knowledge of the rear backing from its surface, where it incidents the surface. That's bizarre, okay? A 50-year paradox. Now, standard optics, the mathematics are flawless. We've tested this in 1,000 different scenarios over those 50 years. We understand and measure optics perfectly. The causal gap is what remains. We can't explain why. The implication is that the bulk material in some way is affecting what's happening at the surface. And we don't know quite how far into that surface the light is entering in order to then be reflected out. Now, we do have very precise timing of light. We know we're not measuring light which has gone full life cycle through to the rear backing plate and reflecting again. So we can discount that. Now, what does expanse tension theory have to offer? Well, let's think about it. We've got glass material, mass, matter with a density. We have maybe backing substrate materials in the rear, again, matter, mass, density. Well, expanse tension theory brings in a real gauge invariant singlet scalar field that couples to the Higgs portal, couples to mass. And that field, as we've described in the channel for gravity and gravitational attraction between mass objects, creates a tension gradient around mass. So the glass itself reconfigures this proposed field in expanse tension theory, reconfigures the field and sets up a tension gradient where mass resists that field and expansion within that field. So where you have a surface of glass, the tension field is actually subject to all of the mass in the experimental setup. So whether you have thicker and thicker bulk glass material, or you start loading in rear backing materials of opaque, rigid plastics or wood or aluminium, what you actually have is just you're adding in mass density. And that's where expanse tension theory can explain what happened. The tension gradient in the field is present on that surface where the glass is striking. And the theory says, you can actually account for the backing material in the way the bulk density has tensioned and deformed, reconfigured that field. Now, there's a paper, I'll link to it in this video. What I do in the paper is explain the paradox in detail, including explaining what is known and what is not known, where the paradox exists. So I explain that. I also then get into what is expanse tension theory and how does expanse tension theory propose to measure sensitivity of the reflection due to either mass density of the material or temperature variation, which temperature, remember, tension expansion reduces mass density, or the varying wavelength of the incident light. Okay. Then the whole appendix, most of the appendix goes into experimental setup that says if you take light and shine in a particular experimental setup, you might be able to detect with the discrimination that this field is present. So you can actually, there's a whole experimental setup to test for the changing mass density, rear backing material, bulk glass thickness, or the wavelength of incident light. And again, the evidence seems to suggest that the difference from the null hypothesis, that light is reflected off the surface of glass without being affected or sensitive to rear backing material, but the evidence suggests not. So that is how expanse tension theory potentially resolves a 50-year-old Richard Feynman paradox. Okay, really clever. I mean, Richard Feynman, wow, he was amazing. He was so famous, and he's left us with this unknown causal mechanism. And a lot of physicists are saying, well, all of the optics, all of the measurements of optics today, we know exactly and precisely we can measure. For me, that's not good enough. As an engineer, I want to know why. Let's get to causal mechanism. Why does this sinusoidal 4% to 16% reflectance change because of material behind the reflecting surface? Read the paper. Hopefully, it's an accessible paper. Lots of images and diagrams to try and explain the equipment setup and how things are changing, to try and be really clear on what exactly is being tested and what is not being tested. So I hope you enjoy and understand the paper. If not, leave me a comment. But here's the important thing from this video. Maybe for the first time, this is a part of expanse tension theory that can be tested within an ordinary physics laboratory. Even a sixth form A-level physics laboratory would even have the equipment to be able to run some of these very low cost tests. Certainly a physics laboratory in a college or a university can run these experiments. And the question is, can we actually find the detection through these proposed experiments? Can we find the evidence that there is a density dependent field that is impacted by the mass density of the bulk material that's then impacting the interference of light and how it causes reflectance from the surface? Okay, what's this for expanse tension theory? It's a proposed resolution. It's not proof, but it's where expanse tension theory plugs in to the causal gap that we have. Now, it uses very, very similar mechanism to how we resolve the Thomas Young double slit experiment. Again, the equipment setup, the slits, suffer the innate tension gradients of this field. So imagine if the Thomas Young double slit experiment and the Richard Feynman glass paradox actually have one single common solution. Wouldn't that be amazing? Okay, thank you for watching. Please share, subscribe, go back to the beginning of the channel if this is the first video. Go right back to the apple orchard and watch the series develop in order as, again, the series develops. If you know somebody who's interested in science, physics, cosmology, please share the channel with them. More importantly for this video, if you know somebody with an A-level physics laboratory or better, college, university or organization with that kind of equipment, please share this with them. They could be a part of proving expanse tension theory field exists or not. Anyway, thank you for watching, and let's leave you with a bit of sunlight because it's still January and we haven't seen it for quite a long time. Okay, thanks for watching. Bye-bye.